This experiment focuses on understanding the relationship between voltage, current, and resistance, as well as how resistors behave when connected in series and in parallel. By applying Ohm's law V equals IR, the resistance of each circuit configuration can be determined by measuring voltage and current and analyzing the slope of a voltage versus current graph. This approach highlights the connection between Ohm's law and the linear form of an algebraic equation. The experimental resistance values are then compared with the theoretical values obtained from the color codes on the resistors to evaluate measurement accuracy and calculate the percent error. In addition, testing different resistor combinations allows us to observe how the total resistance changes in series, parallel, and mixed circuits. Overall, this experiment provides a deeper understanding of resistive circuits and the principles that govern their behavior in electrical systems. The wires were used to build and complete the electrical circuits. The voltage and current sensor measured both quantities accurately during the experiment. The resistors provided known resistance values for comparison between series and parallel connections. The second set of wires ensured proper circuit arrangement for each configuration. The Pasco Capstone reader, used for the first time this semester, collected and analyzed the data to create voltage versus current graphs and calculate resistance from the slope.
We have 3 resistors labeled R, R, and R. Each resistor's theoretical value is obtained from its color code using the standard band chart. After noting these values, we'll measure them experimentally. We start by connecting only one resistor at a time in series with the current sensor and the signal generator, and in parallel with the voltage sensor, we set the signal generator to 0 volts, then increase the voltage in 1 volt increments up to 10 volts, recording the current each time. Capstone automatically plots voltage V versus current I. We apply a linear fit to the graph. The slope represents the resistance because V equals IR gives R equals V I. We'll repeat this for R and record each slope value. Next, we predict which configuration series or parallel will have the higher total resistance. Since current must pass through every resistor in series, resistances add up, giving a higher total. In parallel, current splits, lowering the equivalent resistance. We record both theoretical and calculated values in Table V and prepare to verify them experimentally. We now connect all resistors in parallel and repeat the voltage sweep from 0 to 10 V. Capstone plots the new VI graph and gives the slope, our measured equivalent resistance. Next, we wire all resistors in series and repeat the same measurement procedure. Again, we capture the VI graph and calculate percent error for both configurations. We now examine whether the order of resistors affects the total resistance. In theory, for pure resistors, the order in either configuration should not change the equivalent resistance. If our results differ, we'll analyze possible causes like connection resistance, measurement noise, or sensor calibration and note this in our conclusions. Finally, we build a mixed circuit, 2 resistors in parallel and 1 in series with that pair. We'll repeat the measurement 3 times, each time changing which resistor is in series. For each configuration, we record the slope and compare how adding a series resistor changes the overall resistance. Through these steps, we verified Ohm's law and confirmed how resistor arrangements affect total resistance. Series circuits increase resistance, parallel circuits decrease it, and mixed setups fall in between. We'll now analyze percent errors, discuss deviations, and present conclusions on the physical reasons behind them.
Number 3. First off, we gotta go over the setup of this lab. In this lab, we had to take 3 resistors that we wanted to test. Each resistor had different color bands, which we ended up writing in this table over here. Each band represents either the numbers, the total number of zeros after those 2 numbers, and the tolerance for this resistance. This is the data as shown. We should cover first the concept of Ohm's law and how the experimental value for these resistors will be obtained. As you can see, Ohm's law is stated over here as voltage equals current times resistance. Resistance is equal to voltage divided by current. We can thus state resistance as a slope in a voltage times in current graph. This is how we obtain our experimental value in this lab. First, we tried the first resistance. We plotted the voltage and current and obtained a value of 147, extremely close to our theoretical value of 150 as stated with the color bands in the resistor. Next, we went to our resistant 2. The theoretical value was 270 ohms, also in the color bands. The experimental value, as plotted in the voltage and current graph, was of 279 ohms. A 3.3% error was obtained with such value. Later, we finally calculated our third resistor. The theoretical value was of 1000 ohms, with our linear graph of voltage and current stating that its slope is 983 ohms, which is pretty close to our theoretical value, and thus a percent error of 1.7 was obtained. That's how our resistors behave if they are set up in either a series or parallel order. For a series, we have to put our resistors one in front of the other, while in a parallel order, we have to put them over one another. Here, these formulas give us the total value for either the resistors placed in series or the resistors placed in parallel. While doing our calculations, we arrived to the value of 1,420 ohms for our resistors put in series and 87.9 ohms for our resistors put in parallel. What we will do is that we will calculate the overall resistance of this circuit, plotting voltage and current, obtaining the slope, and measuring that experimental value with our theoretical values of either parallel or series setup. For the series connection, connecting each resistor one behind the other, our theoretical value was of 1,420 ohms, and looking at the graph of voltage and current, we obtained a slope of 1,430 ohms, which gives us a 0.7% error, extremely small. Then we went for the parallel connection, putting each resistor on top of each other. We measured the voltage and current of the total circuit. Our theoretical value for this parallel setup was 87.9 ohms, and our experimental value, as seen as a slope in this graph, was of 87.9 ohms, exactly what our theoretical value stated, giving us a 0% error. For our extra credit, we will do a combination of both the series connection and parallel connection of the resistors. We will get resistor 1 and put it in series with the parallel connection of resistor 2 and 3. Then get resistor 2, put it in parallel connection with resistor 1 and 3, and so on, seeing the variation of the theoretical values obtained through the formulas and the experimental values obtained from the slope in the voltage and current graphs. Number 1 scenario, resistor 1 is placed in series with the parallel connection of resistor 2 and 3. We obtained that the theoretical value of this is 362.6 ohms, as observed in this calculation. We plotted the table, and then we compared it with the voltage and current graph, which gave us 360 ohms in its slope. We calculate the percent error, and it's just 0.7%. For resistor 2 scenario, we placed resistor 2 in series with the parallel connection of resistor 1 and 3. We calculated the theoretical value with this equation over here using the series formula in conjunction with the parallel formula, obtaining 400.4 ohms, and we saw that in the voltage and current graph the slope was 408 ohms. Plotting that in the table and deriving our percent error, which was 1.9%. Our last scenario is resistor 3 scenario, in which we put resistor 3 in series with the parallel connection of resistor 1 and resistor 2. We obtain the theoretical value of resistance as 1096.4 ohms, as seen in this equation. We plotted that on the table, and then looking at the graph, the slope is 1080, which gives us a percent error of 1.5%, compared with our theoretical value of 1096.4 ohms and our experimental value of 1080 ohms. That would be everything for our data analysis. Thank you so much for watching.
For our conclusion in this experiment, we analyzed the relationship between voltage and current for different resistors configurations in order to calculate resistance using the slope of a voltage versus current graph. By applying Ohm's law and comparing the results to theoretical values obtained from the resistors color codes, we confirmed that the slope of the VI line accurately represented the resistance of a circuit element. Our measured resistance for individual resistors were generally close to the theoretical values, with percent errors that fell within the expected tolerance ranges. For the lab, that was 10%, but for our group expectations, we wanted to be within 5%. Small discrepancies were likely due to the measurement inaccuracies, wire resistance, or slight variations in the resistor manufacturing tolerance. When comparing the different setups, the series connection by far produced the largest overall resistance, as expected, because the total resistance in series is the sum of all individual resistance. In contrast, the parallel connection resulted in the smallest overall resistance, since the current has multiple paths to flow through, effectively reducing the total resistance. The experimental values for both configurations matched close with the theoretical predictions within a percentage error within 1%. We also verified the order of resistors in either a series or parallel setups does not affect the overall resistance, which supports the theoretical principle that total resistance depends only on the values of the resistor, not their physical arrangement. For a mixed setup, where two resistors were connected in parallel and one in series, we observed that adding the resistor in series increased the total resistance, while the specific resistor that were used in series slightly changed the overall value depending on its resistance. These results were consistent with our predictions based on the formulas for equivalent resistance and percentage error within 2%. Overall, this lab demonstrated the direct relationship between Ohm's law and linear equations, reinforced how to determine resistance graphically, and confirmed the theoretical rules governing series, parallel, and mixed resistor networks.